Okay, well, this would be section 6.2, 6.3, 6.4. This would be for the lecture scheduled for October 27. And taking that big chunk of the middle of chapter 6, we'll start with this topic called variance. Okay, sum of squares, as we mentioned before, is a good measure of total variation if we are using the mean as a model. But it does have one important disadvantage. This is interesting, and this is what I hinted at before. You probably don't remember, but I was hinting at finding an average of something. So if we have a count on the first top example for group 1, which is fine, there's a mean that they've split down the middle with a blue line. And then for group 2, it looks like they've doubled all the counts. Instead of having 1 and 1 and 2, as I point, and then another one over here, suddenly it's up to 2, and then 2, and then 4. Each count number has been doubled. This has been doubled from 1 to 2. The mean is still the same. And we consider the distributions just by looking at them and taking a look at the sum of squares. For the first one, it is a 14. Okay, we don't need to go into the details. 14 looks fine. But then, because we've doubled all the observations, we've doubled the sum of squares also. Notice how 14 times 2 is 28. That's not good. It looks like it's more variable, but it really isn't more variable. So which looks more spread out? That's a false question. You really can't get that they're the same. So that's kind of a problem. So we do have no situation where they're the same. Which has the larger SS? Well, they're the same. So that's another trick question, so to speak. So we have, that to deal with. And so if they aren't the same, how could they look the same? The spread doesn't look any different between the two distributions, but the one on the bottom is a much larger sum of squares, which is something wrong with that. Now, even worse, according to them, as I zoom on this a little bit, if I can get this to zoom. My pad will not zoom today. I don't know why. Anyway, so just increase the size of your screen, I guess. There we go, got a little bit. So we've got 3 in a row here with a mean of 5. And there's about a 4, a 5, and a 6 with a count of around 30, 35 or so. But then we look over here with values as low as around 1 maybe. The scale isn't very good. And a scale of maybe almost a 10, but much lower counts. And so the sum of squares for the first distribution, or the third distribution, number 3, has an SS of 72, but the third one only has 58, yet it is more spread out. They both have the same mean. They've kind of taken that into compensation. They are not really worried about the mean changing, but they're looking at the spread of the data and how the sum of squares doesn't seem to be doing a very good job right now. So that's a little bit funny. So which looks more spread out? Distribution 3, distribution 4. I think you should say 4. They're definitely looking more spread out. Now the counts aren't very much, but just based on what we have, you'd have to say that 4 is more spread out. So of the distributions above, for which do you think the mean would be a better model? Well, the mean would be a better model for both of them, but here it's a better model for those that are tightly grouped. So distribution 3. And why is the SS so large in distribution 3 relative to 4? Well, I think it's clear that the counts are way higher, and the counts are increasing the SS, the sum of squares. And I don't know if that really is that important. So in effect, we're going to divide by a number close to n to kind of compensate, get an average. Okay, sum of squares worked fine as a way to quantify error around the mean and compare error when they had the same sample size, or even close to the same sample size. But when they're not even close, it is not as easily interpreted. So we need something a little different, some sort of averaging process to make them more comparable. So without that, SS would always grow as the number of data points gets larger. Well, I mean, it might not grow, but it nearly always grows. Yeah, you could find exceptions where it might not, but usually it would. So can you think of a way to measure error that would not be influenced by sample size? I already hinted. What if you just took some kind of an average and divided by n? And turns out n minus 1, as you see in this formula I'm pointing at, that's the better way to go. So we are going to look at variance and standard deviation. And to calculate variance, which just sounds like variability, we start with SS, or the total error, and then divide by the sample size to end up with a measure of average error. The average of those squared deviations is SS's. And so because it's an average, it's not impacted by sample sizes. So it can be used to compare the amount of error across two different samples of two different sizes. Although if you had a sample size of 2 and a sample size of 5,000, there may be other issues with that. But as long as they're, not very far off, it does tend to arrest that kind of situation. So SS is the numerator here, and that's the square deviations, the sum of all those square deviations. And is this a sample statistic or a population parameter? It looks like it's from samples because you've got a sample mean and all the individual y's. And there's difficult to impossible to get all of them anyway, so it's usually sample statistics anyway. Okay, you can see that the numerator is the sum of squares. And to get an average of the square deviations, you would divide by n. We instead divide by n minus 1. This gets a little technical, and they do have a reference that you could try to read. It's not entertaining unless you've read this kind of thing before. But dividing by n minus 1, by simulation and also through theory, it shows that actually gives us a better estimate of the actual variance. Doesn't seem like it would, but it does. And so n minus 1, when n is large, it really doesn't matter very much. If n's 1,000, divided by 999 isn't going to make much difference. But if n is only like 10, n minus 1 is 9. That would make an appreciable difference. So this largely helps, especially with smaller sample sizes. It corrects some kind of a bias. And so it turns out that if you divide by n, with a small, especially a small n, the most extreme values in the population are unlikely to show up. If you divide by n, especially in smaller samples, it would underestimate the variance. Dividing by n minus 1, a smaller number would expand that number just a little bit and make it a little bit bigger, make the variance estimate a little bit larger. Okay, and as it gets larger, we don't care. As we say, when n's 1,000, it makes very little difference, but they still do it anyway. And yes, there's a very entertaining math article to read about that. So anyway, this is the picture we've actually zoomed in on before, and shows the actual squares. The deviations from a mean like 62, and the straight lines, the vertical lines would be the deviations, and if you square them, then you get what's actually in there. I'm going to close the door because of a barking dog. Give me 5 seconds. Okay, I've had Halloween screams with Halloween music, but barking dog drives me crazy. Anyway, that's just me. Here we see a picture that we looked at in the video and we explored SS, which is the visual definition of SS. What is the visual definition of variance? Well, it's a little bit tougher, but one could get at that. And the sum of the area of the squares, of all the squares, looks like SS, and that's what we just said. So it looks like the very first one is all of that. And next, a visual definition of variance. That's a tough one. I'm not sure how you would get that. But the average area of the squares turns out to be the correct one. But that was one that I'm not sure how you would be able to get that. But anyway, I gave you a strong hint, but definitely pick and choose and see. Pretend I didn't say anything and just try it on your own, which is why I probably should just shut up and let you do it yourself. So how do we calculate variance in R? We use var of whatever's inside. And so we have our thumb data from Tiny Fingers. So Tiny Fingers, $thumb. And so they've already done that, and they found the answer. And remember, we divided by a certain number. 82 divided by 5 was 16.4. That's an example we just talked about last time. So yeah, that corrected it somewhat. Okay, so we can do this, and we can go ahead and find var of, well, it's the same thing as before, so I'll just go ahead and copy what's on the inside of the parentheses and get that in there. We can actually go ahead and calculate that. And what's the hint say? Well, the hint says you can use fingers, thumb to use just the thumb column. So we'll go ahead and run that. And okay, it doesn't like that. So we got to get the fingers, I'm sorry, the wrong data frame. So now we've got fingers. Let's go ahead and run that. And there it is, 76.1552, which is what they got as well. Okay, so the correct interpretation of this value, this is an interesting one because it does strike at the heart of what some people think is correct, and these are important problems in that you shouldn't make mistakes like this. To say 76 thumbs that are larger than the mean, No, not close. There are about 76 thumbs that are different from the mean. That's even worse. No, they're both bad. Average squared deviation in the distribution is about 76 squared millimeters. Yeah, yeah. And then the average deviation in the distribution is about 76. No, not far enough. The average thumb in the distribution is about 76. No, that's the mean. No, we're not talking about that. So I think I gave you a pretty strong hint as to what to do. Let's move on to the next section. This one's about the standard deviation. This is the one that we actually use. Variance is really only used by quality control people and people using the F distribution, which was on the schedule for us to teach, but we're not going to get that far. So standard deviation is a better measure of variability, one that we can actually use, and it maintains the same unit. So you're talking millimeters, it's millimeters, not squared millimeters. If you're talking about dollars for economics type of problem, we don't have squared dollars, we just have regular dollars, which is amazingly nice. But there is a square root involved, because if you take the square root of the variance, you will be at the standard deviation. It's summarized by this formula right here. The standard deviation is written as S, and we didn't make a big deal out of it, but S squared was the variance. If you take the square root of a square, because we know the number is positive, we don't have to worry about imaginary numbers here, 0 or positive, then you will get simply the square root of the square. So in other words, we take that formula we just had and square root the whole thing. And so yeah, that will give us a value that we can use, and much more useful than variance. And it's the point in my classes that I've just barely even talked about the variance, because that's just an esoteric measurement that is not really used a lot in practice. Standard deviation is the one that really settles into the groove, so to speak. Okay, we have a visual definition of standard deviation. Check all that apply. This is a tough one. Let me see if I can give you some hints here. Roughly the average residual from the model. I don't know how you would know that, but that turns out to be not a bad answer. Roughly the average vertical distance from the mean. That is exactly the same thing. Yeah, residual vertical distance, that's the same. Roughly the average area of the squares. No, that's getting into the squares, a squared millimeter. Nope. That's more like variance. The number of squares, no, that's like saying n. No, that's not close. Roughly the average perimeters of the squares. Wow, never even thought of perimeter. Where do they come up with this stuff? Okay, let's move on to this one. Remember that the variance of thumb from tiny fingers was 16.4. Which of the following is a good estimate for the standard deviation of thumb from tiny fingers? Well, remember, variance is about 16, and standard deviation is a square root. Remember the square root back here? Square root of 16, everybody knows that's a 4. If you want to get your calculator out and take the square root of 16.4, be my guest, it's a number slightly larger than 4. But either way, they did say estimate. They did not look for a bunch of decimals, fortunately. So yeah, there you go. To calculate the standard deviation in R, although you could do a square root situation, SD sounds a lot better. No, it doesn't stand for San Diego. It does stand for standard deviation. And yes, here's how to calculate the standard deviation of our thumb data from tiny fingers. And so it's the same as before, except we have SD instead of VAR. Tiny fingers, $sign thumb. This is what they did from their tiny fingers model. And there it is, 16.4 square rooted, at least to 6 decimal places, is about 4.049691. So there you are, a little bit more than 4. There are actually a few different ways that you can get the standard deviation for a variable. Once the function SD, of course, obviously, but then you could also square root the variance with a combination of the functions. So this is kind of the longer way to go. They just want to show it to you. And yet another more useful way is to use good old favstats. Try all 3 of these methods to calculate the standard deviation of thumb from the larger, not tiny, fingers data frame. So let's see if we can come up with something like that. Now, what if we typed in standard deviation, and it looks like we could just start with this one. I'm just going to copy it and bring it down by pasting underneath the standard deviation. But I realize that's not the exact one, because it did say fingers, and we don't want tiny fingers. So we just want to cross out the tiny part and keep fingers. Fingers, $sign thumb. SD, standard deviation as they asked. But now, for the second portion, line 3, calculate the standard deviation with square root and variance. And so if we put them kind of like back to back, and let's see, let me copy just the inside part here so I don't get too much copied. There's Command C. But on the outside, what we need to do is make sure we've got square root on the outside, because it's done last, after the variance has been calculated. And then we bring in to the inside of the variance parentheses, Command V, to give us fingers, $thumb. So the data set fingers, the variable thumb, separated by a $. That would be the same thing. Now we could also try, on the 5th line here, 6th line, favestats. So favestats, you can look at your cheat sheet if you'd like. This one insists on the tilde followed by the variable, tilde thumb. And we also have data equals fingers. This is the long-winded one, but it does provide a lot of information. So maybe because it gives you like 9 things at once, maybe it's not so bad. So I think that's all we need. I should have looked at the hint first, but let's take a look at it. Make sure to do it all 3 separate ways and hit run for submitting. Of course, you would submit. I don't have to submit. Make sure you're getting correct values. So let's go ahead and hit run. And something has gone wrong. What has gone wrong? Favestats is not misspelled. Tilde thumb, yeah, I got that, $ equals, or data equals fingers. Yeah, I'm not quite sure what went wrong there. Unexpected symbol. Yeah, okay. It worked just fine yesterday. The same old story. So I can certainly relate to your frustration on the R commands. I would much rather be teaching statistics and let R just be a sidelight, taking up 5 to 10% of my time instead of 70 or 80% of my time. So that's the way it seems to me anyway. So if I, just run it again, let's just submit it. So let's go ahead and take a look at the solution. It's probably just something really small that I've done wrong. SD, fingers, $thumb. I think I got that already. Yeah, SD, fingers, $thumb. Okay, square root var, fingers, $thumb. Yeah, that's pretty straightforward. What happened on the third one? Favestats, tilde thumb, data equals fingers. Data equals fingers. Yeah, you got me. I just have no idea. So have a look at the highlighted code in the editor. And where's the highlighted code in the editor? Is that the little tilde? Favestats. Yeah, wow. I don't know. Anyway, sorry to be embarrassing here, but we do see the answers, and when you type it in, undoubtedly, you will get the exact answers. The standard deviation is 8.72 and change, and the square root of the variance is exactly the same thing. These numbers agree. And then the favestats gives you a lot more information, gives you the 5-number summary to get started, then gives you the mean. But more importantly, right now, we are looking at that measurement of variability called the standard deviation. Notice it does not mention the variance. That is not considered to be all that important. Not for us in the elementary world, and actually in practical world as well. Variance is much more esoteric. What is a squared dollar anyway? What is the correct interpretation of the value 8.72, etc., or around 8.73 rounded? So we could take a quick look at this and see that we have 8.73 thumbs that are different from the mean. Well, no, I don't think that that's going to be correct. Average square deviation is roughly 8.73. Well, we're looking at standard deviation, and that removes the squares. That was the whole idea. One of the ideas, not only to get a better number, but to get the unit that we could actually use. So that was important as well. The average deviation in this distribution is roughly 8.73. Well, that's another way to say it. Standard deviation could be thought of as an average deviation. That's not the way I learned it, but that's the way they're talking about it. And the average thumb, no, that's talking about mean. Nuh-uh. And the sum, where'd that come from? No way. So let's move on. Sum of squares, variance, and standard deviation. We've discussed 3 ways of quantifying error about our model. I'll start with residuals, but they aggregate those residuals in different ways to summarize that total error, which we're hoping will be as small as possible. All of them right now are minimized at the mean. Now, so all are useful when the mean is the model for a countable variable, quantitative variable. So then, what does it mean when to say that these 3 measures of error, sum of squares, variance, and standard deviation, are minimized at the mean, And A says these measures are smallest when the mean is the model. Well, okay. These measures are all equally small, and thus the values will be all equal to each other. Huh? Not necessarily. They could all be small but at different rates. C, these measures are the best measure of error for any model. Maybe. D, the values of these measures will be smaller than other measures of error, such as MAD or range. Well, that happens to be true, but that's not what they were getting at. That's not what they're getting at. So that's not going to help us. Thinking about quantifying error in Mindset Matters. As I get a sip of iced tea here. Below is a histogram with about a weight lost of each of the 75 housekeepers in the Mindset Matters data frame. And notice, when you lose a negative 5 pounds, that is a double negative. And that means they actually gained 5 pounds over here. And these people gained just a little bit of weight. The people at the 0 did not lose any weight at all. And then finally we get over here. Well, this person lost about 10 pounds. And a lot of people lost around 3, 4, 5 pounds. A lot of people did that. So looks like the mean is around 1.5 pounds lost, by the way. It's hard to measure, but it looks like a little bit more than 1. Okay, use R to create an empty model of pounds lost. Call it empty dot model. They love that term. I'd never really heard of it before. And then find the SS, find the variance, and find the standard deviation around this model. So let's see what we come up with. The linear model, LM, is perfect for that. So LM of the variable pounds lost, capitalized lost, and then we'll also set it to null, capitalize the null, and then we'll also say data equals Mindset Matters. And let's see, I'll just copy that here and copy and paste that right after the data. It does not matter what color it's written in, so that should take care of that. Okay, am I missing anything? What if we had the, let's see, I guess we can continue with this. Yeah, let's go ahead and continue with this. If we look at the sum of the residuals, that would be our sum of squares going. So let's do that. Sum on the outside, resid closer to the inside, and that would be of the empty model, empty dot model that is. Make sure we capitalize the E, of course. Empty dot capital model. No, it's not capital. Boy, you have to be very careful with that. Do a lot of copying and pasting, I don't blame you. And close the parentheses, and then let's not forget to square it because they were the squared residuals. So resid gets you the residuals, and now the outside of that parentheses, very subtle, get that caret, and then the 2. And then we want to sum that, so another set of parentheses. This parentheses goes with the sum, the outer parentheses. And so that should take care of the SS part. And then we continue, and they do say there's multiple correct solutions, so you can come up with a slightly different way of this. I'm going to go ahead and get to variance because they did want variance. Remember, I'm checking off this list on line 4. SS is the first one. I just did that. And of course, the empty model, we did that in the very beginning. And now var will come up with that, and then later we'll do SD. So variance would be Mindset Matters. I think that's already copied, but let's go ahead and make sure that's copied and slip that in here and paste it. And Mindset Matters. And the variable after the dollar sign is pounds lost, capital lost. Okay, so we got that. And I'll close that up, and we'll go down and do the same exact thing with SD. And let's see, all that. And so I'll just go ahead and copy this whole thing. It's just a duplicate. I'm going to copy that and put in Control V right here. And I think that's all we need. Let's look at the hint, though. The hint is saying, remember to use null for the empty model. Okay, that's fine. So let's go ahead and run that and see what we get. So looks like they also did an ANOVA command. They did not make that abundantly clear, but let's go ahead and try so we can kind of match what they have. They didn't really ask us for this, but since sometimes they don't, different authors write different parts of these things, and sometimes one of them does a little bit more than the other one apparently. So let's go ahead and put in empty dot model to see if that matches up. Notice they did not really request this. If I run it again, it'll just give me that everything plus the extra line. So there it is. It's got the starting with the this 7.52. It's duplicating the original one, then a 2.74, then this little mini table. Let me X out this line here, and we can see various other things. Okay, so they switched the order for some reason. They've got 7.52, which we got. There it is, 7.52. That's the variance, kind of a less used number to be generous. And then 2.74, that's a much more popular number, and that's a much better number for us. And then we can also take a look at the ANOVA table and learn that the sum of squares was 556, the bigger version is down here. We divide by 74, that's 75 minus 1, by the way, and also that's known as DF, which is also known as degrees of freedom. But meanwhile, the mean square, means SQ, is 7.5. That's also a helpful number to show how things are going. That happened to also be the variance as well. So you can take a look at it from several different angles here, and there are lots of different ways to do this. But 7.5 will get you to the variance through the other angle, so to speak, and then square rooting it will get us to the most useful number, the standard deviation, nearly always a sample standard deviation, especially in this class. Okay, so which of the following are commands would help you figure out SS for pounds lost, sum of squares? Check all that apply. So if we took the variance of mindset matters for the variable pounds lost and divided by 75 divided by 1, minus 1, yeah, I think we just did that. That's perfect. Sum of squares of pounds lost, there is no command for SS. Sum of absolute residuals, that's very busy, but empty model, I don't think that's going to particularly help us so much. And then, well, you can try it and see what happens, but let's try D, ANOVA of the empty model. That's what we kind of did. Remember, ANOVA empty model, that's part of where I got this idea. And yeah, that seems to be giving us SS indirectly. Now, once again, SS doesn't seem to work there, so you can see a couple that do work on that particular problem. Next problem, well, let's see what we have here. Which of the R commands would help you figure out variance in pounds lost? And they all start off with the var command, although notice the spellings and the capitalizations. Here we have a capital var. It doesn't like that. I don't know why it doesn't, but it just doesn't. This is even worse. It's all caps. No way. Now we're talking. This one's a little better, but pounds lost, is that really enough? We're not really sure what data set it comes in, so that's a better one there. But you can try C and see what it tells you. And if they spell out the word variance, well, it doesn't accept that either. So this is the R section of the class right now. Which of the following R commands would help you figure out standard deviation? This is the one that matters for pounds lost. I long time ago, I probably won't get a choice this time, but I got rid of almost all the variance questions in my tests because it's what's the point? We all want standard deviation. As long as you know that one's the square root of the other, then that's all you need, and then we just stay with standard deviation the entire rest of the way. But anyway, this is a different way of teaching it. So let's take a look at this particular one and see if we can figure out what's going on. We could try to guess the R commands, and this one I probably ought to let you try, but favstat seems like that might get us somewhere. SD, once again, the pounds lost seems to be abandoned, kind of like before. Here we have a capital SD. No, that's not going to help us. Here we have the small SD, and this one does have the data frame and the variable. That's looking much better. And SQRT of variance, that's doing exactly the same thing as what we just did. Mindset matters, $ pounds lost. There it is inside the parentheses. But wouldn't it be easier to type in SD versus square root of variance? I mean, they both work, but which one's faster? Yeah, well, E is not wrong, but D is more concise and more to the point. So we have the 556 for the sum of the squares, and that was from the ANOVA table. If we can come back here, 556.7 sum of squares divided by the 74, that's n minus 1. We got our 7.5, which is also known as the variance, 7.52, etc. And the standard deviation was the square root of 7.5, so there it is, around 2.7. That's a very good measurement of variability. Instead of giving you a bunch of examples that explain that variability, this book does not do that. No empirical rule, no Chebyshev's theorem, stuff that would give you. This is like, it goes back to when I started teaching statistics. They would just say, oh, here's a standard deviation. it's a number, enjoy. They didn't say anything about it for like as long as a month. And then a month later, we'd come back to it and say, oh, yeah, here, by the way, this is what it was. I thought they'd solved that issue, but they've kind of gone back in time, back to the old style of teaching. And it's just a different style of teaching. What can I say? It may confuse students just a touch, but they did say something about average deviation. That's not exactly what I would have said, but that'll do for now. It's better than nothing. Okay, match each measure of error to its correct interpretation. Okay, well, we have all these things that we could look at, and we've got a total kind of sum of squares, the total square deviations. A variance is like an average, but we've got the squared pounds for sure, and the standard deviation solves that issue. So that's actually a pretty easy one. And here we have some notation that we could enjoy. We use different symbols to represent the variance and standard deviation. And here we have the sample, the population. This is rather traditional and something I'm certainly used to. And the samples are estimates. They're best estimates of what's really going on, the real overall process in the real world. So here are the symbols, and the mean is often called y bar. X bar is another one that we see. Variance would be s squared. And then, if you do get that, quickly take the square root and get you your standard deviation. That is a pure square root, by the way, so do not worry about n minus 1 on this one. And so s, that's a number that a letter we could really use. Now, sometimes in future problems, you can, excuse me, be given an assumed population mean, such as mean equals 100 or mean equals 70 or something like that. And then we go to the Greek letters, as we talked about. Greek letter sigma, the small sigma, not the large sigma that does summation, because sigma does two different purposes. That can be confusing. The large sigma that you see in sororities and fraternities, that's a summation. This is a little sigma, lowercase sigma, looks like a little script O, but it's an S. Greek does that. And sigma squared, sigma, much more useful than S, but even so, in many of my examples as far as calculations, I've never really gone this route. I've always gone to the S's only because that's the only thing that's practical. And plus technology does it for you anyway, so that's kind of fading out. As we have said before, there are often many different words that represent the same ideas in stats. For example, the mean is sometimes referred to as the average. You see the phrase mean squared error in statistics. What do you think it refers to? Try to figure it out. Well, okay, you've got a mean, you have a variance, you have a standard deviation. I should probably let you go for that yourself, but I will say it's not the mean. How could it be the mean? Okay, variance is the mean squared error. Oh, there it is. And it's an average of the square deviations from the mean. It may be shortened to be mean square or MSE. Yeah, so now we know it just means variance. Same thing for our purposes. And the ANOVA function actually had it as mean SQ, and that is the variance. Just another word. ANOVA can get much more complicated than what we're seeing, and so there's other reasons for this and other verbiage and all this kind of stuff. And now we're up to a very large number. The sum of squares is 11,880. When you divide that by 156, we're getting to a variance, mean square, that is, same thing, of 76. And the square root of that would be around an 8. 8 squared is 64, 9 squared is 81, so it'd be between an 8 and a 9. And of course, when you type in var, or var, of course the ANOVA with the empty model gave us the analysis of variance table, and this time we're looking for the variance of fingers with respect to thumb, and so that gives us this portion of it. So they're just showing you what the commands would do. And we'll move on to our final section of the day, because we try to hit, 3 per day most of the time. And this is an extremely important part, also involving the most important formula in all of statistics, hands down. I think that anybody would say it's unanimously the most important one, and it's sad that we've gotten so far into the semester before we even talked about it. But anyway, we have looked at the mean as a model, and we've learned some ways to quantify the total error around the mean, the spread, and good reasons to do it. There's another reason to look at both mean and error together. When you put the two ideas together, it gives you a better way of understanding where a particular score falls in a distribution. So a student called Zelda, amazing how they picked Z, has a thumb length of 65.1 millimeters. What does this mean? Is this a long thumb? How do we know? By now you may be getting the idea that just knowing the length of one thumb doesn't tell you very much, especially if you had nothing in the background. That'd just be kind of like, whatever. So interpreting the meaning of a single score helps us to know something about the distribution that the score came from. Specifically, we need to know something about its shape, center, and spread. So in addition to knowing Zelda's thumb length is 65 and some odd millimeters, we also know that the mean is 60. That helps. What does this tell us that we didn't know before we knew the mean? And it does not say check all that applies. So let's take a careful look. A says, we now know how long this thumb is relative to other thumbs in our sample. Kinda, let's keep moving. We now know how long this thumb is relative to other long thumbs. Well, what is a long thumb? That's missing the mark. C, we now know this is one of the longest thumbs in our sample. No, how would we know that? We'd have to see at least some kind of sample. We don't even have the sample yet. All we have is the mean and one value. How about D? We now know this thumb is longer than average, and that's about it. Okay, it's about 5 millimeters longer by subtracting, but we don't know what the spread is. We just don't know. We don't have a very clear idea how to judge 65.1. It still might be considered to be kind of close to the mean, or maybe it's far from the mean. It really depends on how tightly bunched the other thumb lengths are. Okay, so these three choices, which of these measures of spread might be most useful in determining how far 65 millimeters is from the mean? Well, let's see. You've got the total squared area total squared error called SS, 11,880, compared to 65. How would that help us? Yeah, you'd have to get out some formulas and do some fiddling, but instead of that, let's just keep looking. Variance. Well, this is better. 76 is the variance, the average squared error, but we want to get down to units so we can actually work with. Nothing like standard deviation. Yeah, standard deviation, the average error is 8.7. That tells us like a unit of variability. And so now our 5, the difference of 5 from 65 down to 60, can stack up against the 8, or 8.7. So that's a lot better. It doesn't tell us everything, but at least we're getting started. So SS can be really useful later, but for this purpose it stinks. Yeah, not even close. 65 and 11,880 don't look like they belong in the same universe. Yeah, reminds me of the Cauchy distribution, where you get 1, 2, 3, 5 billion, 6, 7, 8, negative 13 trillion. There are distributions like that that are rather predictable 90% of the time, and then just suddenly there's an earthquake and things go crazy. So then you can't really predict very much based on them. But anyway, I divert myself from the main topic here. Variance is useful, but the units are still hard to interpret. Yeah, we don't want to use square millimeters. Standard deviation is the winner, obviously. And so here we have some colors here, and we can take a look at the mean, 60, and then Zelda in red. So Zelda's 65.1 millimeter thumb is shown in red. Get a better picture. There it is. And you can see how she's a little bit bigger, but still kind of in the middle of the pack. Above average, yeah. Not real above average. 90's way above average, for example, way over there. So we can combine the mean and the standard deviation. And we can coordinate both of them to interpret the meaning of an individual score. And so we have an extremely, with a capital E, popular thing called the Z-score. Yes, very popular. If I had my way, I'd be putting this all over the next test. So don't skip this section. Say you have a video game called Cargill. A friend of yours says their high score is 37,000 points. Is that good? How do you know? If the average is 100,000, that's not too good. If the average is 1,000, sounds real good. So we need to know what the mean is, and it wouldn't hurt at all to know what the standard deviation is, or some measure of variability. Standard deviation is the best one. So let's say you know that the mean score across all players is 35,000. So this person's a little bit above it. Now notice the other subtle difference here that doesn't really come up until later. Mean score across all players of the game. And this person's high score is 37. They're really comparing apples versus oranges, or all-time highs versus typical situations. And that's not quite the same. It's like comparing the World Series versus just a plain old regular baseball game. World Series is on in just a little while. That's why I said that. So how would that help you? Clearly it would help. You would know the score would be 37,000 is above the average by 2,000 points, even though we do seem to be comparing slightly different things. Let's kind of ignore that for a minute. Even though it helps you to interpret the meaning, we need to know the variability, how far above the average it is relative to the whole distribution. And what's similar about the 37,000 and the 65 millimeters? Well, they're both above average, but at first you don't know how far above average. Is it just slightly above average or is it way above average? Those details are not immediately apparent. And so we say that this distribution of the scores on this Cargill game is represented by one of the histograms. Both of them have average score of 35,000, but the distribution on one of them has a standard deviation of 1,000 points, and the other one has a standard deviation of 5,000 points. Let's take a look at them. And this one has a tight standard deviation. It's distribution number 1. Standard deviation is only about 1,000. This one has a very wide, flat, squished pancake kind of distribution, standard deviation of 5,000. And yet, the blue line, the mean, is exactly the same, and the red line for this particular person is exactly the same. So if the true distribution of the Cargill scores is the one on top, what would you think if your friend scores 37,000? I'd say it's pretty good. It's not the best of all time, but it's pretty good. Almost for sure in the top 10%. By the way, the Z-score does lend itself quite well to finding out where you would land on a percentile basis. Everybody's taken scores like SAT or ACT or maybe GRE, and you get to see a percentile, and it tells you how well you did. And this person would probably be in the 80, 90th percentile, just eyeballing it. Whereas this person might be in the 55th or 60th percentile. The 50th percentile is right at the mean. I hate to mix messages, but those of you who know what percentiles is, this would be better than the mean, above maybe 60% of the total, the rest of the way to the left of them, but below about 40% of the total. That's not quite as impressive. I mean, it's above average, but this is way above average just based on the low variability of the players here. The high variability tends to blunt the deal because we kind of expect the deviation to sway back and forth more with a wide variability. Okay, what's the true distribution on the bottom? Well, on the bottom, it's not that impressive, as we mentioned. So it's still okay, but just okay. It's not super great like it was in the pointy distribution that we see up here. Alrighty then. So clearly your friend would be an outstanding player if the first was true, and if the second was true, it would be slightly above average. So here is a way of writing Z. There's a better way, but we'll have to use this one for now. I'm not able to write on the screen right now. I'm just trying to figure that out. We take a particular value, yi, subtract the mean, y bar, and divide by the standard deviation. Sometimes you could say x minus x bar, but they like y's, and that's okay. So it's kind of the same idea. But the main way to do it is in words, is to take your value, subtract the mean, see if it's positive or negative, and that's great. You know if you're above the mean or below the mean just by looking at that number. But if you divide by what's in the standard deviation, then you can see a lot more of what Z would have to offer us. And we'll get more on that in just a minute. What's the numerator in the formula above? The value minus the mean, well, there's a name for that. It's called the deviation. Don't make it too difficult. We're taking some of these into account, but the numerator is just going to be the deviation, of course. What's the denominator? Well, that's super easy. There it is right there, so I'm not going to tell you that one. Don't miss it, but it'll tell you if you got it wrong. See if you can explain what Z means just by analyzing the formula. Well, as I've said, they will say very soon, it'll be the number of standard deviations you are above or below the mean. And then one can go to get probabilities or percentiles from that, but that's not today's lesson. Let's apply this formula to our video game score of 37,000 based on the two hypothetical distributions. And we'll try the one with a 1,000 standard deviation. To refresh your memory, that's the visual look up here. With a 1,000 standard deviation, we're talking about this person being way over, probably involving a larger Z-score compared to the next one that we'll do later. So divide, and you can see this, 37,000 minus 35,000 is 2,000. 2,000 divided by 1,000 is exactly 2. Well, that's an easy calculation, and we can kind of do the same thing down here as we get to the next line. And you can just copy it if you want, but I'll just type it in. Do not put extra commas in, it doesn't understand them. So it can subtract the two numbers. The numerator is not changing, but be sure to divide by the number that has the wide, flat distribution. And then we're just going to run it because the hint just says to calculate the difference. But in parentheses, yeah, you can't skip the parentheses. They do comment on that to see what happens. So here we have, in the case where this person's a very good player, z-score is 2, which is 2 standard deviations above average. That's very, very good. I can tell you that puts them in the 97th percentile. Yeah, it's very, very good. Whereas 0.4 or 4/10 of a standard deviation above average, yeah, that's pretty good, but it's nothing special. So that's what's going on. We don't have probabilities directly assigned to them yet. And so what z-scores do we get? Well, they're just right in front of you. 2 for the first one, 0.4 for the second one, and they're replayed right there. In both cases, the numerator is the same, and that's a gap of 2,000. The 37,000 minus the mean is 2,000. The denominators are what's changing, because we've got 2 of these smaller standard deviations, or 0.4 of the wide standard deviations. Dividing by a bigger number results in a smaller output. I've just been saying that for my 1101 crowd because they're involved in finding divisors for such as the House of Representatives or the Electoral College, a very topical topic. I wish we had topical topics that had to do with Election Day in this class. We don't really have them. They did have something in the Jupyter notebooks, but we're not really doing those right as of the moment. But it wasn't really what you think it was. Okay, so we have the standard deviation of 1,000, versus standard deviation of 5,000. So they show what we just kind of talked about. Now, why do we put parentheses? Well, we had to keep the numerator together. Yeah, that's all there is to it. You got to do that. Get that numerator first. Find that 2,000 gap, and then divide by 1,000. If you do it the other way, what's going to happen is you can get something ridiculous. When people forget their parentheses, which I'm sorry to say did happen on the exam, watch your parentheses very carefully. When in doubt, use them. It doesn't hurt to use too many, but it does hurt to use too few. Now, of course, if you mismatch the parentheses, that's a different story. But anyway, 35,000 divided by 5,000. If you did that one first, got a 7 out of that, and 37,000 minus 7 happens to be 36,993. That's a z-score? Nope. Z-scores usually stop around 3 or 3.5. In most realistic terms, z doesn't really go outside that window of plus or minus 3.5. Hardly ever. That's where tables actually stop, because it just doesn't really go any further than that. And to get a 36,000 and change is ridiculous. So that would be garbage. So yeah, but if you don't type in anything, it's going to go ahead and divide first, and then it'll go ahead and subtract. So if you don't even put any parentheses in, it's going to do this by default, because it likes division better, and it does that first. PEMDAS, division, PEMDAS, I'm sure you've heard of it, and it likes division ahead of subtraction. So yeah, in order to fight that, you must put the numerator in parentheses, or it just won't understand you. An alternative would be to find them separately line by line, but that takes too long. We don't want to do that either. So interpret these z-scores. They are measures, but what kind of unit of measures? 2 standard deviations, 0.4 standard deviations, above or below the mean. Because they're positive, they're above the mean. And if you're 2 above the mean, we saw the visual interpretation, that is a better score. Harder to do. So it's the number of standard deviations, a score is above or below the mean. In boldface is a very, very important definition that you have to memorize. No doubt about it, you have to memorize this. So start doing that. Because if you don't know what a z-score means, that would be kind of a bad thing. So if the units are standard deviations, that's for sure. And there we just said all that stuff. Now compare the scores, which is more impressive. Based on the picture's worth 1,000 words. Clearly the z is much more impressive, much harder to do. Puts you in the top, say, 2 or 3% of the crowd versus the top, say, 40% or so. The z-score of 2 is much more impressive. Yeah, so it's harder to do that than it is to just stay kind of in the middle and be a little above average. So what's the difference between a z-score and a standard deviation? I don't really think of these, but the z measures the number of standard deviations. So standard deviation is like z equals 1. And here, z could be anything, technically, but usually stays within the bounds of minus 3.5 to plus 3.5. That's just some free information that they forgot to talk about, but I'll go ahead and tell you. So it's roughly the average deviations of all the scores in the mean. Yeah, I guess that happens to be true. That's not the way I would define it, but okay, because we're not talking about some other things. That'll have to do for now. And it's the spread of the distribution. How spread out is it? Those pictures really say a lot, so I'm so glad that they use them. The z-score uses the standard deviation as a ruler for measuring how far each individual score is above or below the mean. It's like a ruler. Depends how tightly bunched it is. And the z tells you how many of those there are away from the mean. By the way, if z equals 0, you're sitting right on the mean. So if your score was 35,000 and the mean was 35,000, there's not much to calculate. Z equals 0, which says you're right on the mean. Okay, and let's use z-scores to help us make sense of our thumb data. Get a sip of tea. Okay, so we have the following. Let's use z-scores to make sense of the data. Calculate the z-score for a 65.1 millimeter thumb. So we can try to write some code for that. And we've got thumb stats is defined as favstats with the variable thumb from the data equals fingers. So if we can in here type in the value 65.1, and there's a decimal point that is, and you put parentheses around it, almost forgot, get the parentheses there, 65.1, that's subtract, and put a space in there, make it easier to read, and then thumb dot stats, make sure it's spelled correctly, of course, and then $mean. So the variable is thumb.stats. Well, actually, it's coming from thumb.stats. We're only interested in the mean. So that gets us our numerator, the value that we have. This is the mean from our data, 60 point whatever it was. That takes care of the numerator. To get a z-score, we're going to have to divide by something. That something will be the standard deviation. So as we put parentheses down, and look for thumb.stats again, but this time we're interested in finding the standard deviation from that. So $SD. Ought to take care of it. What does the hint say, by the way? You can access values in thumb.stats by using the $ operator. For example, thumb.stats, $mean. So thumb.stats is bunched together. The $ separates it. So let's go ahead and run it. Don't forget to submit it when you think you're done. This apparently is a z-score of 0.57. Typically, z is rounded to 2 decimal places, but yet, of course, they give you 7. But it's a little bit more than a half of a standard deviation above average. So this person definitely has a bigger thumb than average. Is it hugely bigger? Not so much. Might be in the top 40%, 35%, something like that, based on my recollection of these things. So what is the correct interpretation of the z-score? This one is very, very important. I should probably let you do it, but let me see if I can talk about all these options. The thumb is bigger than 0.57 of all thumbs in the population. No way. Occasionally you hit coincidences, but they are only coincidences. The thumb is 0.57 meters long. Meters long? Wow, that's a pretty big thumb. Huge thumb. There's a 0.57 chance of picking a bigger thumb, a thumb that is bigger than this thumb. No, that would put it actually below average. That's not even close, and it's not even correct anyway. The thumb is 0.57 millimeters longer than the mean. No. This thumb is 0.57 standard deviations above the mean, which happens, by the way, to be less than 1 standard deviation above the mean. So it is above the mean, but not huge, not a huge number. So a single z-score tells us how many standard deviations away this particular thumb is from the mean. Because the standard deviation is roughly the average distance from all scores of the mean, is likely that most scores are clustered between 1 standard deviation on the high side and on the low side. So above the mean and below the mean. In fact, one could easily say that around 2/3 of the data will fit in that little range between 1 and -1 for your z-score. Now, we don't have a picture to go with that. I wish I could just suddenly sketch you one. I'm sorry, I can't quite do that yet. But yeah, that's correct. Roughly 2/3 are in between those values. I believe it's 68%. It's less likely to find scores that are 2 or 3 standard deviations away from the mean. In fact, to get above 3 standard deviations away from the mean, you're talking about 1 chance in 1,000. That's why tables typically just die out at that point, because there's nothing much more to say. But z-scores do give us a way to characterize scores in a bit finer way than just bigger or smaller than average, which is rather coarse, better than nothing. But z-scores gives you even more information. If we get to the probabilities, which we can't quite do yet, then we've got even better information than that. Z is kind of a middleman to get you to those probabilities. One more use for the z-score is to compare scores that come from different distributions, even if they're from different scales. So this is a very nice thing, kind of like the box plots when we had the 2 box plots side by side, or even 3. You can kind of see what's going on amongst different groups. So distribution number 2 represents the distribution of scores for the players of Cargill. We know this distribution is roughly bell-shaped and normal, and the mean score is 35,000, the standard deviation is 5,000, and your friend just scored 45,000. What is her z-score? Well, don't really need a formula for this if you look at it from these nice round numbers. The difference between 45,000 and 35,000 is 10. 10,000 divided by 5,000, don't use your calculator here, it's 2. We had a 2 from before, but the scores were different. This is the one based on the extra wide flat one, so I'm trying to draw my cursor in a really flat bell curve. So yeah, z-score is 2 there, and they say that right there. 2 standard deviations away from the mean, not too many scores up there, you're in the top 2 or 3%, as I said. So another friend who doesn't play it at all, she plays Spargle, or is it Gargle? I can't remember, but anyway, it may be similar, but it has a completely different scoring system. The scores on Spargle are roughly normally distributed. The mean is only 50, that's not much fun. Standard deviation is 5. And so this person has a high score of 65. So it's funny how they compare average scores with high scores. They kind of miswrote that, but anyway, don't worry about it. If we want to know which friend in general is a better gamer, the one that plays Cargill, the one that plays Spargle, one can figure not too difficult here because the numbers are not very unfriendly here. 65 minus 50 says that they are 15 points above normal. But the 15 points doesn't say much until you divide out the standard deviation. 15 divided by 5, yep, that's a 3. 3 is very, very good. You're in the top 0.1% at that rate pretty much. So that beats out a standard deviation of, or a z-score of 2, which is very good, but the standard deviation of 3, that's extremely good. Extremely good. And you just don't hear about 4s and 5s. You just don't ever see them. So as I shrink this down so you can actually read it, here we have the summary of the results we just had. And so the Cargill player got a z-score of +2, and Spargle +3. Even though the numbers seem a lot smaller, we are putting it on a comparable formula for z, and that we can see how many standard deviations they are, both above the mean. I can compare the abilities of these two players, even though they play different games. Assuming that they're similar enough, one could still make some observations based on it. And you could say that one's a better gamer than the other because you got 3 standard deviations above the mean. In what sense is Spargle player a better gamer? Well, yeah, because they did so much better than expected. A very tight standard deviation, and she got 3 of them to get to 65. 5 times 3 is 15. 15 above the 50, that's 65 right there. So it doesn't sound like very many points, but so many of these games had just put on an extra 100,000, put a bunch of zeros in the back, and yeah, that does seem a little bit artificial to me. Can you think of a reason why, despite the z-score advantage, the Spargle player may not be that better gamer? Well, they have some hints here. I've got my own comments, but Spargle could be a much easier game, and people tend to be novices. Maybe they're just moving on to the better game, getting away from chutes and ladders and starting to play chess or something like that. So maybe the Cargill player is better, even though her z-score is lower. She's being compared to a more awesome group of gamers. That could happen too. You can get in say a tournament where all the best players just happen to be in your bracket. Oops, no, you're not going to last very long. But if you get into the easy bracket, well, you can just clean up and then won't have any competition until the finals. That kind of thing, if you know what I mean. And also, they were comparing high scores versus average scores. That's something they forgot. But high scores could be an anomaly. They're not the same as the average, not usually. So unless you've only played one game, then I guess it would be. But yeah, so that could be an issue too, and could be that they're just radically different games and don't really use the same skills as well. So anyway, that's the idea. Okay, well, we've talked a long time today and I got through 3 sections. We're going to get through 3 more next time. So we were in 6.2, 6.3, 6.4, and next time it looks like 6.5, 6.6, 6.7. That'll be the live lecture for Thursday, Wednesday and Thursday, I should say. So I'll have a cloud link for that shortly afterwards, and we'll be getting ready for our test schedule for November 10. Haven't heard anything, haven't had a meeting in a while, but I'm sure we'll be getting that together very soon. I'll pass along any information I have as far as that's concerned. So Yes, fall is in the air. Finally, it seems like we go from 90s, and I hear it's going to be in the 30s in a couple of nights, at least in this part of Riverside. So, yeah, that's quite a change. I'm going with my sister's who lives up in Crestline. It's supposed to be in the 20s up there. So, yeah, it's fall's just hit very quickly all of a sudden. So, summer lasted too long, so I'm happy to see fall. And it'll be back in the 80s next week anyway, so it'll be pretty much mild temperatures and daylight time. Don't forget to change your clocks on Halloween night. Late Halloween night, we get our hour back, so get an extra hour on Halloween. That'll be kind of nice too. So as always, if you have questions, please email me. Please work on the material, the chapter quizzes. Be sure you're doing all your R work and anything else you can come up with. And if you have any comments, certainly on Wednesdays, good time to talk to me. I've got lots of hours available. Come on by, happy to talk. And obviously, email will take care of many things as well. Okay, so I guess that'll do it for now. I'm going to see if this recorded. I sure hope it did. Have a nice weekend, or have a nice week coming up. Bye-bye.